Morning. We are continuing our discussion in Chapter 2. This is lecture number 14. I'll cover some topics of Chapter 2 today in lecture 14, and then I will post lecture 15, which will finish Chapter 2. So you can look at the web page for due dates, which are posted, and also I am adding to the problems that are due for the Chapter 2 problem set as we go. So I've got the first and second problem sets. There will be one from today and one from lecture 15 as well, and then we will have that due and we'll begin on Chapter 3. All right, so getting back to Chapter 2, we have been talking about strain as being a change in length if we're talking about axial strain. So lateral or axial strain is a change in length. Now we know that it could be due to a change in temperature, or it can be due to a change in temperature, or it can be due to a stress, a normal stress. So let me ask you a question, and this is just a thought problem that I think you can answer. If we have a structural member and we pull on it, put it into tension, and we get some amount of an elongation of the structural member along, let's call this the z-axis, the x-axis. Now let's call this y, just for kicks. This is generally what we do. And this out. So we're getting an elongation along the x-axis. In terms of the size and shape of this structural member, if it elongates this way, what do you think is going to happen? If it elongates on the x-axis, what do you think is going to happen on the x and the y and the z-axis? Axes. Yes, it will. It will shorten, exactly. So there is some in a homogeneous material. There is some shortening in, let's just say, y and z if the x-axis is elongated. And similarly, if we scrunch it up in the x-axis, if we put it into compression here, and it gets a little bit shorter, then what do you think will happen on the x, on the y and the z axes? If it gets shorter on the x, it'll get a little bigger in the y and the z, won't it? Okay, so in a homogeneous material, there's some shortening in the y and z direction if x is elongated, and there is some expansion in the y and z if x is compressed or shortened. Okay, and the idea of this, different materials behave differently. Different materials have this change in epsilon, or the change in the strain on the y and the z axis for different, I don't have to put del, I can just put e, for different epsilons x. And the ratio of those two things, epsilon x over epsilon y, or epsilon x over epsilon z, this is referred to as axial strain. And the other two axes, or the other two, well, I guess I would say the other two coordinate directions are referred to as lateral strain. And this is always a negative, because if this is positive, this is negative, If this is negative, this is positive. And so the negative of that quantity is assigned the Greek letter nu, and it is called Poisson's ratio. So Poisson's ratio tells you how much strain will, how much the dimensionless lateral side will change based on a change on the axis. And it's important to note we are not talking about del, because if you remember, epsilon is equal to del over L, right? And the length on the axis is going to be significantly different than x on the or L on the lateral side. So we have to make sure that we're basing this on the dimensionless strain, not the dimensional del, okay? But basically, we can use Poisson's ratio to determine what that value is. All right, so we already know that along the axis, epsilon x, for strain induced by sigma, strain from sigma, that epsilon x is equal to sigma over modulus of elasticity, just from this, right, from this graph. Okay, so we know that E is equal to this over this, and if we solve for epsilon, we have this equation. So now that we know that epsilon x over epsilon y is equal to the negative of Poisson's ratio, we can also say that epsilon y for homogeneous material will be equal to epsilon z, which will be equal to the negative of Poisson's ratio times that axial stress over the modulus of elasticity. Now, we're using the elastic equations here, so we have to be within the elastic region. So we cannot exceed, just like with all the other things, we are making an assumption that we're not exceeding the elastic limit of the material. In other words, once we yield or become plastic, these equations do not work. It only works over here in the elastic region. But that's an underlying assumption of everything that we do in this class. We're really only designing in the elastic region. All right? And we will work an equation using this, but Poisson's ratio comes in handy in a couple of different applications. Now, we have to be pretty careful of our coordinate system, and I'm moving forward to section 2.5 right now to talk about something that's called generalized loading. Now, these problems are a little more complicated, not mathematically in terms of difficulty, but there's just a lot going on. But what a generalized loading condition means, instead of just having a single force and a responsive force directed along one axis, what if we have a load or a sigma on every axis? So we're going to talk, we're going to say P is equal to, or sigma is equal to P over A. So if we define our coordinates as y, x, and z, and the reason I'm changing is just because this is what your authors use, so I don't want to confuse the issue. But that means that the direction here, we have some sigma in the x direction, we're pulling, but we also have a sigma in the y direction and a sigma in the z direction. In other words, we're pulling on it in three different axial directions, or we have components in those axial directions. What we find is that the strain on the axis, on the x-axis, for example, is going to be, the way I have it drawn, positive from the sigma x, but we're going to have a little contracture from sigma z and sigma y, and the same on the other three axes. So we have a generalized equation of epsilon x, or the change on the x-axis based on these three conditions of loading. Basically, that it's going to be sigma x over E minus sigma y times Poisson's ratio over E minus Poisson's ratio times sigma z over E. And we have a similar equation for each of the coordinate directions. So what I'm basically saying is the overall change in dimensionless length on the x-axis is equal to the pull that I'm giving it in the x-axis divided by epsilon, or divided by the modulus of elasticity, minus the changes that are occurring on the other two axes. And the relationship between those two is Poisson's ratio. Poisson's ratio tends to be quite small. And once again, these are tabulated values, but because there's not a great deal of change based on Poisson's ratio. But the number for Poisson's ratio may be, let's see, typical values of Poisson's ratio are about 0.25, meaning the change on the lateral axes, and this is just approximate. In other words, the change on the lateral axes, and I should say of epsilon on the lateral axes, is much smaller than the change on the axis itself. So in other words, where you're pulling, that's going to cause the most change in length, but there's going to be a small amount based upon what's going on the lateral axes as well. All right, so we're not really going to spend a lot of time working with those equations, but it's an important thing to note. And in terms of execution, whenever you're using Poisson's ratio, always make sure that you're talking about epsilon and not del. That seems to be the biggest mistake that I see students make. Okay, so now we've talked a lot about normal stress and axial strain. But what happens in terms of shearing stress? Well, we've talked about this just a tiny little bit, and we've said that shearing stress leads to a shearing strain. Now, where this is linear, in other words, an elongation or a contraction, this is angular, meaning that we change the overall shape of an object based on shearing strain. So as you recall, or shearing stress, excuse me. As you recall, shearing stress acts parallel to a surface. And so if we look at this, this is a little analysis technique that we'll be using in the future. This is called a stress block. So we're just looking at a tiny little piece, a finite element of a structural member. And a shearing stress would exhibit itself this way, in that, remember when we had an axial load, it would look like this. Now, if you look at this particular type of an axial load and a sigma, you can see that one force directly opposes it and results in static equilibrium. But if you look at tau, if I apply a force here and a force here, my forces are balanced, but what's going to happen to this block if I don't oppose it? Is it going to sit still? It's going to move. It's going to move. It's going to rotate, isn't it? So that means that for tau, if I have two forces like this, I have to have two opposing forces like this. Sorry. Okay, so this would tend to make it rotate clockwise. This would tend to make it rotate counterclockwise, and therefore all of the taus are opposed, and we will attain static equilibrium. But for that reason, This could be thought of as being sigma x. In other words, it's axial. This is not axial. This actually acts on an entire plane. So it doesn't act on the x-axis or the y-axis, but rather it's acting on the xy plane. So what happens when we expose a stress block to a tau? The sort of deformation that occurs, this is greatly exaggerated, but looks like this. In other words, we have a change not in the length, but in the angles of this stress block. And if this angle before, because we've defined it as a sort of a rectangle or even a square, this angle previously was either 90 degrees, or we would think of it as being pi over 2 in radians. Okay. The new angle here, this is smaller than that. This is pi over 2 minus gamma, which is the change, right? And this angle would also be pi over 2 minus gamma. And this angle would be pi over 2 plus gamma. Very good. I was hoping someone would see that. Very good. All right. And gamma is the amount of change in the angular relationship of those sides of the stress block, and therefore that is the shearing strain. Now, when you compute shearing strain, make sure to measure this in radians. If you're given the degrees if you're given angles in degrees, you have to convert. Okay, and you can always remember that in a circle is 360 degrees, or pi radians. The other thing that you can remember is that a radian is a fundamental measure. That means it doesn't really have a unit. So if you find radians in a final answer, you can just remove it from the equation. Yes? Pi over 2 is 90. Yeah, it is. Thank you. Pi is 180. So you can say 180 degrees is equal to pi radians, right? So you can use that as a conversion factor. Thank you. All right. So here's another little relationship, and I'm building on our relationships and what we know about normal strain and normal stress. We know that in the elastic region, that sigma and epsilon are in a linear relationship for a homogeneous material, for a normally behaving material, and that the slope of that line is modulus of elasticity. So I'm going to start by saying that E is equal to sigma over epsilon. Now if I do the same sort of a plot for that a normally behaving material being subjected to shearing stress, and if I plot that against shearing strain, I find that for some amount of that relationship, it's also linear, and that the slope of that line is referred to as G, which is called either the shear modulus, or sometimes it's referred to as the bulk modulus. This is the better term, in my opinion.
I have a question.
Sure.
It's just the graph that we have for the amount of pressure a material can have before it starts to permanently
Yes,
change.
yes.
Is that like all the way down to an atomic level, where you have all of your atoms are all lined together? And
Yes.
it takes so much pressure before they actually realign with the atoms.
That's exactly correct. And what really happens, Dane, is that after yield occurs or breakage occurs, the material becomes unpredictable because something fundamental has changed. Now, sometimes that point of change will be different. For example, if the material is repeated to, if it's subjected to repeated loading cycles, even if you stay in the elastic region, you can deform it on an atomic level or on a physical level below that number. Or if it's left out in the weather and the material weathers, you know, you've all seen, like, you know, let's say wood gets rotten. You know, if you leave it out, it just gets dry and rotten. So where this occurs is we're talking about a new material that has not been subjected to repeated loading cycles. Okay?
So if you had like a material that was that, you would just have to, let's say it's metal, you just have to melt it back down so it can realign it.
That's exactly right. And we were actually, there's some really interesting properties like that. Now, this isn't to do with the material, but this is something I was reading about on Sunday with lithium-ion batteries. You know, lithium right now, lithium has some really interesting properties, but it's a rare earth material, and so it's not found in huge quantities anywhere. So you only need a little tiny bit, but you got to mine a lot of dirt in order to get that little tiny bit. And it's also quite difficult to extract from ore. So one of the main sources for lithium right now is hydrothermal pools, where if you have a formation that contains lithium, lithium is a metal. If you look over at the periodic table, it's just right above sodium, isn't it? And I know when I do this, the mic, you can't hear me on the mic very well. But anyway, so lithium is right here. So the same sorts of things that will remove sodium or split sodium away from chloride, for example, putting it in solution, will dissolve lithium from whatever you need it to be dissolved from as well, whether it's lithium chloride or lithium carbonate or whatever. Anyway, right now we have an abundance of lithium that's available in the world. We were talking about what about recycling lithium batteries, because you may have noticed, like in your phone, yes?
Because of the all lithium batteries.
Yes.
This is still technology out of the 20th century, and because we're used so much, we will get very many resources.
Very many what?
Problems with the resources of the.
Absolutely, and that is exactly correct. And economic geologists right now are starting to think about that. You know, because right now we have an abundance, but what happens when we don't have an abundance? And so they've looked into ways of recycling lithium batteries, which are not economically necessary right now, but I think it's going to become necessary. And there's a lab in California where they've developed a technique for recycling lithium batteries. Now, you may have noticed, like if you have your cell phone, after it gets a little bit old, you'll notice that like when you charge up your battery, it will get hot, or if you're doing something, you know, you're doing a lot of stuff, it gets hot. That's what's happening. What's happening is the lithium matrix is actually breaking down. But so this lab in California posed the question, how effective could that lithium be if I did exactly what you're describing, melt it down and start over again? The answer is almost 100%. Yeah, so that's kind of cool. Yes, sir?
The thing is, we have to find a way to save energy without chemical.
Very true. Yeah, to store it. Battery storage right now, like, boy, I could talk about this for a long time. You're so true. What you're saying is so absolutely true. Now, the grid, which when we talk about the grid, what we're talking about is how electricity is transmitted in a particular entity, whether it's a state or a government or a country or whatever. The grid in Europe is a little different than it is here in the United States. But in the United States and in Europe both, we transmit with alternating current. But in Europe, and I'm not sure what the voltage is in Germany, but in most countries it's quite a bit higher. We 220? Which one? 230, yeah. See, and that's like in London, in England. I think in most countries in Europe, it's a lot, the voltage is a lot higher, which means that power is delivered more quickly, I guess you would say. And so if you take an American appliance, even if you just get a little converter, if you don't have a transformer, you can actually burn up anything that generates heat, like curling irons. In Europe are notorious for like blowing up if you plug them in without using a transformer. Hair dryers, shavers are another one, like electric shavers, but most people don't use those anymore anyway. But anyway, having said all that, transmission of electricity is something that we developed methods for a long time ago. But storing electricity is very, very difficult, and that's what you're talking about. We have, and anything that stores electricity is traditionally referred to as a battery. So there are wet cell and dry cells and liquid batteries and chemical batteries. One type of battery that is being looked at right now, there's a place in Pennsylvania that's developing, it's old technology, but they basically just have big cans of salt water and they're using them as batteries. They're not aesthetically very pleasing, and they're huge. But, you know, for certain applications, industrial applications, they make a lot of sense. But to carry around your cell phone and have it be small and to not have, like, this humongous battery attached to it, is that right? Don't even carry around a bucket of salt water with you that's electrically charged, right? So, you know, there's some problems with this. But yeah, it's one of the holy grails of engineering research right now, is building a better battery. And better may be different for different applications. You know, fitness of purpose is really what we're talking about. But you're right. I mean, storing electricity right now without chemical means, that is like the thing. And if you can figure that out, you may be like a multi-zillionaire, and really, you know, we don't really need the richest man in the world. That's right. Or woman, the richest person in the world. So, yes.
Aren't they focusing on graphene and other forms of materials?
They are for me, you know, and there's, how would I put this? You will learn, which is very interesting to me as an engineer, that getting an idea and implementing that idea are two different things. And the purpose of science is to develop a lot of ideas. The purpose of engineering is to, like, take those ideas and make it happen. So there's a lot of steps between understanding how that, or why that would work, and actually making it work. And then not making it so expensive or so big or so hot or so whatever, you know, that would have problems. But yeah, so they are looking at some metamaterials. There's a lot of different things out. I think this, to me, like the cans of salt water are really exciting, even though it sounds really boring. I think that's a really cool battery storage for certain applications. But there you go. I like all kinds of power. I like windmills. I like solar panels. I like coal. Sorry if anybody's offended by that. I think, you know, hydro is super. I just love it all. But we really have, in our country right now, we have the wherewithal to make a lot of power. We don't have the wherewithal to store a lot of power. So, and the grid, like I was talking about, the American electricity grid has essentially zero storage capacity. Everything works in a dynamic, it's a dynamical system, it's overspecified, and it's chaotic. It requires input. I mean, even to this day, people at dams and people at power plants are like getting on the phone and calling each other to move power from one location to the other all the time. The only thing we have is what's in the grid at any one time. Now, it's a slight oversimplification. There are some storage facilities, but the amount of power that we store is quite tiny. So there you go. So there's your first project. You guys can get together, make $1 zillion, right? So, and make life better for everyone. So it's like the two things we're going to do in engineering: make a bunch of money, make life better. So there you go. So, and I mean, I've thought about this a lot, and so have many, many other people. But something will happen. You know, the center will reveal itself if people keep working on it. So, you guys keep working on it. There you go. So, anyway, yeah.
Maybe not at the moment.
Right.
Okay. We know how to store electrical energy. Is there even an approach or an attempt at storing like thermal? Because I know we can like get rid of it.
Like geothermal, you mean?
Or just any type of thermal. Like the biggest problem right now is that 2/3 of the energy from an engine is vanished.
It's called a turbocharger. Yes, we do, which I also love. I love turbocharger. But anyway.
These engines we use will have no future, just
Internal combustion, you mean? Yeah. So when you take thermodynamics with me in the spring, you will learn some things about this. I mean, on a very remedial level, we can't get into a lot of it, but yeah. So thermal energy is a really specific thing. Energy has, to give a short lecture that you'll learn more about, energy has both a quality and a quantity. So you can't take every kind of energy and turn it into work, which is what we're talking about. Work requires a very high quality energy, which once again we'll define later on. So you can take some of that, but there's like a point of diminishing returns on using thermal reservoirs. And some of it's environmental and some of it's just design. So we actually look at efficiencies not only in terms of the total amount of energy produced, but in terms of the quality, so that you can sort of determine what has to be spent just for the pleasure of making that work, you know. But like one example I like to use, which is very trivial, but I think it will illuminate a little bit, is like if you look at burning gasoline in an internal combustion engine, the process itself is extremely inefficient, even in a great engine, you know. But if you take gasoline and you convert it to making your wheels go down the road, the conversion is about 30% or maybe 40%. So in other words, you're essentially wasting 60% of the energy. Now I'm using that word wasting in air quotes because you're not really wasting it, but that's the cost of doing business. So why do we do it? Well, because we want our car to go down the road more than we want a bucket of gasoline, right? That's the factor. Or burning corn. Like I burn corn to heat my house because, like I said, I like energy in all different forms. So, and it works for us because my husband grows corn and then we burn it. So, you know, there you go. But it doesn't work for everybody. But why? It's a very inefficient process. You can burn beans, you can burn lentils, you can burn barley, you can burn anything. Anything that has a carbohydrate can be burned to generate heat. So it's very inefficient to burn any substance, even wood pellets. Wood pellets are horrible. Corn, any of it is very inefficient, but why do we do it? Well, it's because I have a stock tank full of corn and I want my house to be warm. I don't have any cows to eat I do have some cows, but I want that corn more to heat my house than I do to have a stock tank full of corn. So do you see what I mean? So there's more considerations than just what the efficiency is. And it's kind of like that with that thermal heat that you're talking about. You can regenerate some of it, but beyond a certain point, you're getting this little narrowed window of stuff, and you're requiring more and more equipment to get it. So there's a point of diminishing returns where it's not worth it. And worth it figures into the environment, how good the equipment is, the cost of everything, and so forth. How's that? Those are engineering explanations. You talk to a scientist, you're going to get a different explanation. So, yes?
Toyota developed an engine with 41% mechanical output.
With 41% output? See, that's very high. That's really, yeah. There's some limits. 41% is not the limit, but there are some more than theoretical limits, but there's some functional limits on how efficient you can get. But that would be great. I mean, if you think about the number of people that drive cars, if you can increase the efficiency of a car from 38% to 41%, and you do that for everybody, you've just saved a boatload of petroleum products. You know.
Have you seen that one? I think it's $2,000 to put into your car, but it actually goes through your fuel.
Yeah.
And breaks up the nitrogen of it.
Right.
And makes it last like 1 gallon.
Yeah, I'm not convinced about it. I actually have an older friend in Phoenix that had one, and I don't think it really worked. I watched it, and I talked to him about it, and I'm like, I think this is a toy. I don't think this is really, I don't think we're helping anything. But anyway, but those are all great. You know what? One of those things is going to work. That's the way research is. You know, some of it might be a con, some of it might just be something fun to put on your car, and something might really make a difference. So keep at it. That's what keeps engineers coming to work in the morning, not in the paycheck, which I am not devaluing a paycheck. All right, so the last thing I want to tell you today before I end my lecture is, if you think about it, in a generalized loading condition, if I have a little stress block, I may be subjecting it to some axial stresses, and I may be subjecting it to some shearing stresses, and I may have some other things going on. But basically, we have three constants of a material: the modulus of elasticity, the shearing modulus, and Poisson's ratio. This has to do with what's going on the axis. This has to do with what's going on the lateral face, and this is the relationship between what's going on the axis and what's going on the lateral face. So it may stand to reason that these three things are not independent of each other, that they are related to each other, and basically it turns out that if you know two of them, you also know the third. So for a normally behaving material, I'm going to not go through the derivation with you, I'll just present this. It turns out that the shear modulus is equal to the modulus of elasticity divided by 2 times the quantity, 1 plus Poisson's ratio. So if you look at this equation, you can see that if you know E and G, you can find nu. If you know nu and G, you can find E, and so forth. And that's for all normally behaving materials in the elastic region of behavior. All right. All right. So do you guys have any questions at this point? All right, well, let's call it a day for now. What we have finished is up through section 2.8. We will not talk about 2.9. We also skipped a discussion of, it's called dilation of bulk modulus, 2.6. So we skipped 2.6 and 2.9. If you look in your textbook, any of the sections that are indicated with an asterisk means that those are optional sections. And if anybody's interested in talking about those things, I would be happy to discuss them with you, but I'm not going to test you over them, and I'm not going to assign you problems over them, just because we got a lot of ground to plow in this class, and so we just keep moving forward with what's the most important. All right, so do you guys have any questions for me? All right, then, let's call it a day. Your next lecture, this is lecture 14. Your next lecture 15 will be posted by Friday, but we will not have class in this classroom on Friday, but lecture 15 is the, you can watch it at your leisure, right? So if you wake up at 2 in the morning and think, gee, I'd really like to do a little mechanics and materials, there you go. So, all right, you guys have a great day.